All right, so this is the first set of notes for Unit 4, which is going to be all about a macroscopic view of the atoms. The unit we just finished was a microscopic view where we actually looked inside and learned about those protons, neutrons, and electrons. But now we're going to start looking at as a bigger picture. So there's two big questions we're going to be answering during this unit. That is, what are the different ways that atoms can combine, and how do we measure them? So if you think back, the first part of these notes is going to be classification of matter. And so far we've talked about states of matter. So before we jump into today's new stuff, I want to kind of review that. So we've talked about 3 different states of matter. And those are solid, liquid, and gas. What we haven't talked about yet is how we can model those different states of matter, and that's going to come into play today with what we're talking about. So I want to real quick just go over our basics of how do we model a solid, a liquid, and a gas. And we call these model of matter diagrams. So we abbreviate it as MOM diagrams. And again, that stands for model of matter, which is what we're talking about. And these are going to get more complex throughout the school year. Today we're going to start off really basic, and then we're going to add to it throughout the rest of the year. So in the most basic form, you're going to have to model different states of matter. So remember, solids, you tend to be compact. You can put stuff on them. They don't take the shape of their container. They just, whatever shape they are is the shape they are. So when we're modeling solids, we're going to draw the particles as touching, because in solids, the particles tend to be close together. That's why I'm on a table right now and I can't put my hand through it because the solids are touching each other. They're very close together. They're also organized, which again is what allows them to keep their shape no matter where you put them. So for example, if I was going to draw a solid, I would draw my particles, which in this case I'm going to represent as a square, touching and organized. Liquids, on the other hand, are still touching. The particles are still touching each other, and that's kind of what allows them to flow still. But what helps with that is that they are unorganized. This is why if you take a liquid, you can put it in several different containers, and it'll take the shape of whatever container it's in. It's not organized like a solid where no matter what room I put a desk in, it's always going to be desk shaped. Liquids take the shape of whatever container they are in. So that's why they are touching, but still unorganized. So I'm going to use circles this time. I'm going to keep those particles touching, but now they're unorganized. They kind of look like they're flowing. Lastly, we have gases. Gases, particles are not touching each other. That's why we can walk through the air or wave our hands through the air. It's because there's lots of space between those particles, and you can move right through them. They're unorganized just like a liquid though, because gases will fill up whatever container you put them in. So they'll get bigger or get smaller depending on the size of your container. So gases are not touching. And they are unorganized. So this time I'll use triangles, not touching, not organized, floating around out there. So that's just kind of real basic introduction to MOM diagrams. We'll get a little bit more complex later on in this video, but do remember your states of matter. We have solid, we have liquid, and we have gas. You might want to find a place to copy this down because we will use this idea for the rest of the year. So let's jump into the actual meat for today. So we've got classification of matter. So we're going to start out by talking about what is matter. So we've talked about states of matter so far, but the actual definition of matter is anything that has mass and takes up space. It has to have those two qualifications in order for it to be considered matter. So some examples of matter would be like water. Water has mass and it takes up space. A desk. People. We could go on and on and on. Take a moment and see if you can think of any other examples of matter. Now, some examples of non-matter are, so anything that doesn't have mass or take up space, or either, would be light, sound, heat, etc. And if you think about it, these are all forms of energy. So energy does not have mass, does not take up space, so it's considered non-matter. And we will deal with those kind of things later on in the year. So we can break matter down into two main categories, and those two main categories are pure substances and mixtures. So we're going to start with the pure substance side. Pure substances are made of one thing throughout. So you could look at it and be like, this is water, this is carbon, this is sodium chloride. The whole sample will be made of one thing throughout, and it's generally made out of things that are found on your periodic table. So if you haven't dug your periodic table out yet, you're going to want to do that. So if it's found on the periodic table or made up of things that are on the periodic table, it's going to be considered a pure substance. On the other side, we have mixtures, and that's two or more substances that are not chemically joined, meaning that they should still be relatively easy to pull apart. So for example, trail mix. If you're eating trail mix out of a bowl, it's relatively easy to pick out the yucky raisins and just go for the M&Ms. That's because those are not chemically joined, so they are easier to pull apart in the end, but they're a mixture of multiple things as well. So we're going to dive more into the pure substance side first. So you should get ready to write these things down on your note packet. So for pure substances, we can break that down even further into two categories. So on the left side, we have elements. Elements are a single thing that's found on your periodic table. So if you can find it as an element on your periodic table, that is an element which falls under the pure substance category. So for example, that could be hydrogen is a single element. It could be oxygen. It could be carbon, neon, etc. Those are all examples of individual elements. So elements are a pure substance that is a form of matter. So we're kind of getting our categories more specific as we go down this flow chart. So in these boxes down below, we are going to practice some more of those MOM diagrams that we talked briefly about at the beginning of this video. So when we're modeling an element, because an element is a single thing that is made up of the same stuff throughout, we always model an element as one single shape. So for example here, if I was going to draw an example of an element, so let's do sodium. And let's draw it as a solid. I'm going to draw sodium as one shape. And then as we talked about at the beginning of this video, solids are always touching and organized. So I'm going to take a single shape, such as a circle, and I'm going to draw it touching and organized. And that would be an example of sodium solid. The solid, one shape, one element, but drawn as a solid, so those particles of sodium are touching and organized. The other type of pure substance we're going to talk about is a compound. Compound are two or more elements that are chemically joined. So if it's a compound, that means they are bonded together, several elements bonded together. And bonds are very strong, so they take a lot of energy to break sometimes. So that's why they're chemically joined, and that's the difference between what we just talked about with mixtures, which are not chemically joined and are relatively easy to separate. Compounds are not. So two or more elements that are bonded together. So some examples there could be water, which is H2O, two hydrogens and an oxygen bonded together. Carbon dioxide, which is CO2, so one carbon bonded to two oxygens. Glucose, C6H12O6. Or sodium chloride, which is table salt, would be NaCl. Those are all examples of compounds. You notice they're all made up of two or more elements that are on your periodic table, but they are bonded together with other elements. So that's what makes it a compound instead of an element. But if you have a sample of salt, for example, NaCl, it's going to be NaCl all the way throughout, which is what still makes it a pure substance, but now it's a compound because it's two or more elements. So again, going back to these MOM diagrams, now because we have two or more things, we're going to draw two shapes. And because they are bonded as a compound, we're going to draw them bonded in our bond diagram. And we show that bond by drawing a little dashed line between them. So for example here, if I was going to draw, we'll stick with salt. If I was going to draw sodium chloride as a solid, I see that it's a compound, so I'm going to draw two shapes bonded together. So in this case, I'm going to do a square, and then to show that bond, I'm going to draw that line connecting it to another shape. So in this case, I'm going to do a circle that's filled in. So that represents one molecule of salt. So one square bonded to one circle is one molecule of salt. So to draw it as a solid next to another molecule of salt, I need to draw another whole one of those particles. So I'm going to show them touching. So you'll notice I'm going to draw them touching, but not bonded because it's a separate molecule. I'm going to connect that to another circle, and then I can just repeat that. So that would represent 4 salt compounds as a solid because they are touching and organized. So that's an introduction to pure substances. Now we're going to go back and we're going to look a little bit closer at mixtures now. So remember, mixtures are 2 or more substances that are not chemically joined. So that's different than a compound because a compound is chemically joined. They're bonded together. These are things that are mixed together in the same container, but are not bonded to each other, so we can separate them. There's 2 different types of mixtures. The first one is a homogeneous mixture, and the second being a heterogeneous mixture. When we're looking at a homogeneous mixture, what that means is that we have an even distribution of substances throughout, meaning in the container, everything is evenly distributed. So if I were to take a scoop out of one side and a scoop out of the other side, it should be made up of the same amounts of each thing when you pull it out. Now that's not necessarily meaning that we have the same amounts total of each thing in the container. It just means that what we do have is evenly spread out throughout that container. So some examples could be Kool-Aid. If you make Kool-Aid correctly, you mix it in and all of that Kool-Aid powder dissolves, and every sip of Kool-Aid you take should taste the same. It should have the same amount of Kool-Aid powder to water ratio, to sugar ratio in each sip that you take. Now that's not saying that you used the same amount of Kool-Aid powder to the same amount of water when you made the Kool-Aid. That would be nasty. That would be more of a paste. But every sip should taste the same if you have evenly distributed that Kool-Aid powder throughout the amount of water that you have. Another example would be sugar water or salt water. Anything where it's going to be the same throughout the entire thing. Now, when we draw homogeneous mixtures, I'm actually going to split this into 2 categories for your mom diagram. So if I split this box in half, we're going to draw 2 different examples here. The first one is if we have a homogeneous mixture that is a mixture of solids. If we have a mixture of solids that is a homogeneous mixture, you want to look for a pattern. So, for example, if I was going to mix iron with sand, which is silicon dioxide, that's the fancy name for sand, those are all going to be solids. So I'm going to evenly distribute those by drawing them in a pattern in here. So iron, if you think back to the last slide, is an element. So I'm going to draw iron as a square. And silicon dioxide is a compound, so I'm going to draw that as a compound. So I'm going to draw that 2 shapes bonded together. So I'm going to do a circle bonded to a triangle. So I'm going to mix those iron particles with the sodium dioxide, and I'm going to try to draw it in a pattern so that it is evenly distributed. So I'm going to start with an iron square. I'm I'm going to put that next to a silicon dioxide. Again, those are not bonded together. The silicon dioxide's bonded because it's a compound, but I'm just drawing it next to the iron because the iron is not connected to the silicon dioxide. That's why we could remove those iron pieces if we wanted. So I'm just going to kind of repeat this to make it into a pattern because, again, we want it to be evenly distributed. And then I'm just going to switch it for the next row. So if you look at that, I see a pattern, and that tells me this is going to be an even distribution. If I was to take a scoop from the left and a scoop from the right, you should get the same ratio of things in each scoop. Now the second category I want to talk about here is what's known as an aqueous solution. And that's just the fancy way of saying a solid dissolved in water. So we see that a lot, like sugar water would be an example of that. I have molecules of sugar and I have dissolved them in water. You can't see them anymore, they're no longer there. That would be an example of an aqueous solution. Aqueous or aqueous, depending on who you talk to, sounds like aqua, which is water. So if we do an example here, we'll do salt water. So salt, again, is sodium chloride in water. We draw this a special way to show those sodium chloride molecules being surrounded by the water, being separated from each other, which is why we can't see them anymore when we draw them. So sodium chloride is a compound, so I'm going to draw that as two shapes bonded. So maybe this time I do a filled-in circle to a filled-in triangle. And then when we draw aqueous solutions, you're going to have to draw a lot of water. So to save ourselves some time, we're going to draw water as an X, just to make it easier on ourselves, since you're going to be drawing a lot of it. I'm going to change that actually, though, not to blue, because I don't want it to blend in as much. I'm going to change it to a different color, so it's easier for you to see. So I'm going to start by drawing a couple of those sodium chloride molecules. So circle, bonded, to a triangle, and I'm going to draw that separated from another salt molecule because, again, they've been separated, they've been dissolved. Throw the third one in there just for funsies. And now I'm going to start putting the water in there. So the water, again, we're going to draw as X's, and the water is going to surround the salt particles and separate it from the other salt molecules, which is why you can't see them anymore, but they are still there. So that's an example of an aqueous solution. An aqueous solution is a homogeneous mixture because those salt molecules should be evenly distributed throughout that water mixture. Now the other type of mixture is known as a heterogeneous mixture, and that is where there's an uneven distribution of substances throughout. So that means that you might have like a chunk of something in one corner, or a large chunk of something in a different corner. If you take a scoop from one side and a scoop from the other side, you won't get the same amount each time. Unlike the homogeneous mixtures where, again, every sip you take should be the same, heterogeneous is it might be different because it is an uneven distribution of substances throughout. So some examples of that could be trail mix. Again, every handful of trail mix you take, you're not going to get the same ratios of things every time. You're going to get a different amount of raisins. You're going to get a different amount of M&Ms. You're going to get a different amount of peanuts. So that makes it a heterogeneous mixture. Another example would be like if you had a bowl of Lucky Charms. You're not going to get the same amount of hearts, stars, and horseshoes every time in every scoop. So those are unevenly distributed throughout the bowl of cereal. So when we're drawing a MOM diagram for a heterogeneous mixture, we're going to try to draw it with no pattern to it. So maybe chunks of something in a corner. Again, we want to try to show that uneven distribution. So if I was going to draw a example of this, we might have, we'll just do something with triangles and squares bonded to circles. So I might have like 3 triangles over here, and then we might finally have a square bonded to a circle. There might be another triangle over there, but maybe then it's another square bonded to a circle with a triangle here, another triangle. So if you look at what I just drew here, There isn't really a pattern to it. If you take a scoop from the left and a scoop from the right, you're not going to get the same ratio of things each time. So that's our classification of matter, and you are going to have some practice with that. We are going to use this for quite a while, so and especially the MOM diagrams. So make sure you take a look at this and understand what you're doing before you move on. Next, we're going to talk a little about physical and chemical properties. So physical properties are any property of a piece of matter that can be measured without damaging the object. So things that we can observe that can be measured without damaging the object. So some examples could be mass. We can weigh the mass without damaging the object. You just put it on the scale. Volume. You've measured several volumes at this point without damaging anything. Color. Smell. Size. Shape. Melting point, which is just the fancy way of saying the temperature at which a substance will melt. That's known as the melting point. So there's many more examples in this, but you kind of get the idea. Physical properties are anything that you can measure without damaging the actual object. Now, on the other hand, chemical properties are properties that damage or destroy an object in the process of measuring. So an example could be flammability. How do you test if something is flammable? You light it on fire, and if it lights on fire, it's flammable. If it doesn't, it's not flammable. But either way, it's not going to come out the same when you're done. Another example could be reactivity. So if you take a liquid and you dump another substance in there and you see if it reacts, that's going to destroy the object, because either it is going to react and form something new, or it's not going to react, and now you have two things mixed together that now change the properties of what you have. Durability. So if you see how durable something is, you're going to have to try to break it. And in the process of doing that, you're probably going to break it. And again, that's damaging or destroying an object. So again, you're going to get more practice with these, but these are just some examples of the difference between physical properties and chemical properties. Now, along those same lines, we have physical and chemical changes. So physical changes are changes where no new substance is formed. Okay, whatever you have made, whatever you have done to this, there's nothing new there. It's still the same thing. It might be in a different form, but it's still the same stuff you started with. So some examples of physical changes would be a change in state. So we talked about states of matter at the beginning of this video. So for example, if something goes from a solid to a liquid, it's still going to be whatever that substance was. It just is in a different state now. So still the same object, so that makes it a physical change. Another example might be if you decide to paint something. It's still the same object, it's just a different color. Or if you cut a piece of paper in half, it's still paper. It's just now in two different pieces. So those are all examples of physical changes, things that we can do to an object where we don't end up making anything new, but are still a change. Now, on the other hand, we have chemical changes, and that is where a new substance is formed. So a couple examples could be a chemical reaction. I mix two things together and I make two new products. That would be a chemical reaction. That would be a chemical change. I've made something new. We just talked about fusion and fission. Made new elements when you did that. Baking. You put a bunch of ingredients together and it comes out a cake. You've made something new. A chemical change has occurred. So some indicators of a chemical change, some things you can look for to decide if it was a chemical change or not, especially when you're in the lab, was there a temperature change? Now that could be up or down depending on what type of reaction we're doing. Was there light given off? Was there a color change? Were there bubbles that were being produced? Was there a gas being made? Those are all some indicators of a chemical change. So you're going to work a little bit more with this in our next lab too, that you guys are going to be working on the next 2 days. Last thing, another thing to look for is there's a thing called the law of conservation of matter, or the law of conservation of mass. And this says that matter cannot be created or destroyed it can only change form. Okay, so we can't create or destroy matter, we can only make it change where it's at currently. This also applies to mass. So what that means is that the total mass of the starting system must equal the total mass of the ending system, even if that mass has changed forms or locations. Okay, we can't gain or lose anything in a chemical reaction. It has to still be there at the end. It might be in a different place, but we have to, it's conserved, it is somewhere. So that was a real brief introduction, Notes 1, conservation of matter and classification of matter. If you have any questions, please let your teacher know, but there is a worksheet in your homework packet that goes with this.